Hey everyone, I'm Nick, and welcome to another episode of Advanced Topics. So in this episode of the series, we're going to be talking about duplicate filtering. So when we're optimizing applications, we're often looking for ways to do less work. And one of the ways we can approach this problem is through algorithmic optimization. So we can try and find a different algorithm that leads to a smaller total number of operations, which hopefully improves our performance and execution time. Now we're going to be looking at algorithmic optimization in the context of duplicate filtering today. And to motivate why you might be interested in this problem, consider the scenario where you have an input vector of elements, and you're going to process each of the elements in the vector. So you're going to pass each element to some process, method, or function. And let's say that that function or method is relatively expensive, right? So the computation is expensive. Now, if you're a performance engineer, and you're trying to make your application faster, there's a couple different routes you might go. So one thing you might consider is there any way for me to optimize this function in order to decrease the processing time per element? That's a perfectly valid strategy, but it's not what we're going to focus on today. Another thing to note is you may have already done that, so it may be very difficult to optimize this method or this function much more, right? Now, another strategy that you might look at is you might consider, is there any way for me to process fewer elements and decrease the total amount of work that I have to do, right? And that's where this duplicate removal or duplicate filtering comes in. So there'll be situations where, for a particular function, for identical inputs, you get identical outputs, right? So if you pass the number 2 to a function, you get a result. If you pass the number 2 again, you get the exact same result. And when we have cases like this, one optimization strategy we can employ is instead of calculating a result for every single value, right, or every single element that we need to process, we can build up a table of results. That way, when we see a new value come in, right, instead of automatically just processing that element, we can check to see if we've already computed a result for this element, right? So we can keep a cached copy of the results, right? A table of these results that we can index into instead of always having to do the computation, right? And this can be a very useful strategy, provided that the cost of doing something like building this table or filtering out the duplicate values or figuring out if a value is a duplicate isn't prohibitively expensive. So if we're going to be doing something like duplicate filtering, so trying to find just the unique values that we want to process, we need to make sure that we do this effectively and efficiently. So let's go ahead and look at our example today. It's in this duplicate removal.cpp. This is all written using Google Benchmark. And we're going to look at a few different implementations of duplicate filtering algorithms. So we'll be looking at a brute force implementation and some more clever ones. And we'll be studying the performance of these algorithms under a few different conditions. So we'll change the size of our input vector of integers. So we'll look at different sizes of inputs from a vector length of 2 to the 10 up to 2 to the 12. And then we'll also look at these vectors with different ranges of input data. So we'll have random numbers from between 0 and 10 in some of our vectors, and then all the way up to random numbers between 0 and 10,000 in some of these cases. And we'll try and study the performance differences as we swing these two knobs or turn these two knobs. So let's go ahead and start by talking about this baseline benchmark. So this is going to be our brute force implementation. So the setup to our benchmark is pretty simple. We create our vectors, right? So our input vector vin, which will contain all of our input data, including duplicates. And then we have our output vector vout, which will contain just the unique values. Then we go ahead and fill our input vector vin with the random numbers based upon our distribution. And then we have our main benchmarking loop down here. So this is what we're actually going to be timing. So as you can see here, our code for this brute force implementation is pretty straightforward and simple. We start out by going through every single element in the input vector. So we do for auto I in vn. For every single one of those elements, we check to see if it's in the output vector, right? We check to see if we've seen this number before, and we've placed it in our list of unique values, which is our vout vector. So we use std find to check to see if the value I is in vout. If it isn't in vout, right, that means we've seen a new number. That means that what studFind returned was vout.end. So if it is a unique number, we add it to vout, right? So we do vout, and we push back I into vout. If we have seen the number before, that means studFind returned something other than vout.end. So we go ahead and just continue to the next element in vn, right? If we've seen this element before, that means it's a duplicate. That means we don't need to add it to vout. A pretty straightforward implementation. And then each iteration of this timing loop, we go ahead and clear our output vector, right? So we can reprocess it. Okay, so that's going to be our baseline implementation. So let's think about where this might get slow and where we might think about performing some optimizations. Now, if we think about what we're doing each iteration of this outer for loop, this loop where we're going over all the elements in our input vector, the amount of work we're doing each iteration of this loop is monotonically increasing, meaning the amount of work we do each iteration is either staying the same or increasing over time, right? So why exactly is this the case? Well, we have to think about what we're doing in here, and specifically about this studFind. So this studFind here, where we're looking to see if I is within vout, this is really just another for loop. It's a linear search over our output vector vout. So we're looking for I within vout. How do we do that? We iterate through the elements in vout and compare them against I, right? And see if they're the same. Now, this can get pretty expensive, right? As vout increases, right? As the length of vout increases. That means each iteration of this loop, we're going to have to do more and more work as vout gets larger and larger and larger as we find more and more output elements, right? And we'll see this when we start looking at the performance in just a few minutes. But that's something we might want to look at here, right? This O in complexity to check to see if a value is unique or not. Okay, so if we're already saying that this O in complexity or this linear search of vout is bad, how might we make it better, right? Or how might we improve this algorithm? Well, we can try using a different data structure. So instead of using something like a vector to store our unique values and filter out all these duplicates, we can maybe try something like an unordered set. So now we're looking at this benchmark called unordered set, where we have our input vector of integers again, vn, but instead of an output vector of integers, we're going to be using an unordered set of integers. Now, an unordered set is an associative container with unique keys that are mapped to buckets, right? Now, the nice thing about an unordered set is that the process of finding something in an unordered set or inserting something into an unordered set is a constant time complexity. It's basically the time it takes to hash the value of the key to map it to a bucket, right? And duplicate values, right, or key values that are the exact same will get mapped to the exact same bucket, right? So they basically all kind of override each other and go to the exact same bucket if we have duplicates. Okay, so how does this implementation work? So we set up the problem much the same way. We create our data structures, we fill our input vector with our random numbers based upon those distributions and the vector sizes we saw before. And then we have our main benchmarking loop, which is even more simple this time. It's really just a single line of code, or one or two lines of code. So we go through all the elements in our input vector, right? So for auto I and vn. But instead of checking to see if something is inside of our unordered set, all we need to do is insert everything into our unordered set. Right? All we really need to do is insert all the values, because when we insert a value, the hash function, well, we'll get our mapping of this value of I to a particular bucket, and duplicate values will all go to the same bucket. Right? So they'll just all override each other. So what we'll be left with inside of our unordered set is just all of our unique integers, right? Our unique values from our input vector vn, right? So that's how we can implement it with an unordered set. Now we've changed the problem slightly here. We've changed it from I have an input vector and I have an output vector to now I have an input vector and I have an output unordered set. Now there'll be situations where you can do this in your code base, and there'll be other situations where other code is going to rely on your output of this function to be something like a vector, right? So we should take that into account. And that's what we're going to do on our last benchmark called Unordered Set Copy, which looks very similar to our Unordered Set benchmark, with the exception that we also have an output vector vout. So, we create our data structures at the top, we fill our input vector with random numbers, then we have our benchmarking loop. Now, we filter our data in the exact same way as our unordered set implementation. So we just insert all the values into our unordered set, but now we're taking into consideration the time it takes to copy all the elements in our unordered set into our output vector vout. Right? And of course, we clear our output vector and filter each iteration, right? So that they're clear and we're starting from a blank slate every single iteration. Okay, so those are our 3 benchmarks. Let's go ahead and take a look at what the performance looks like and see if we can find any trends. So we'll go ahead and quit out of here and we'll compile duplicate removal. And we'll do it with a whole bunch of optimizations. So O3, march, and mtune equals native, and link time optimization. And let's go ahead and run and see where we kind of wound up and see if we can spot anything interesting. So as you can see here, we have our baseline implementation running right now, where the first value, 10 here, is the input vector size, so 2 to the 10 elements. And the second number here is the max range of our random numbers, so random numbers between 0 and 10, then 0 and 100, 1,000, and 10,000. Then we increase our vector size to 11, and then 12. And we've got our other benchmarks running, so our unordered set and our unordered set copy just finished up. So let's start by looking at our baseline, right? So this was our brute force implementation where we were doing that ON complexity stood find every single iteration of that outer for loop. So we'll start by looking at the performance trends as we increase the vector size, ignoring the distribution of our data, right? So if we just look at, say, the random numbers between 0 and 100, and we compare our 2 to the 10, 2 to the 11, and 2 to the 12, we see something rather intuitive here from a execution time perspective. As we increase the number of elements we need to process in vn, our execution time, of course, increases as well. We have to process more elements. So we go from taking about 14 microseconds for a 2 to the 10 size vector. This goes up to here, about 34 microseconds for a 2 to the 11 size vector, and then about 73.4 microseconds for a 2 to the 12 size vector. So we're a little over doubling the execution time every time we double the size of our vector. And that's somewhat intuitive, right? If we have to process twice as many elements, we'd expect it to take about 2x the amount of time, right? Pretty simple. Okay, but a really interesting thing here has to do with when we change the values that are being stored in those vectors. So as we increase our random numbers from between 0 and 10 to between 0 and 100, 1,000, and then 10,000, we see a huge change in performance for a constant sized vector, right? So all of these cases are with a 2 to the 10 size vector right here. And our execution time increases from 2.8 microseconds up to 14 microseconds, up to 60 microseconds, and up to 95 microseconds. So, we're getting towards the range of being over 40 times, getting close to 45 times slower between our random numbers between 0 and 10 and random numbers between 0 and 10,000. So what can we use to explain this? Or why is our execution time increasing so much? Well, this really comes back to what's going on every single iteration of that for loop and how the size of vout grows as we change the data distribution. So if we only have random numbers between 0 and 10, we can only have at most 10 unique values, right? There's only 10 values, 0 through 9, when we generate those random numbers. So the size of vout is capped relatively low, right? Versus if we say have random numbers between 0 and 10,000, right? Now we could have, many more that potential values inside of vout. So vout can grow quite large, right? It can't quite grow to 10,000 in this case because our input vector size is only 1024, right? But it can grow pretty large, right? And same thing goes as we increase from 10 to 100, 100 to 1,000, and then 1,000 to 10,000. We're increasing the likelihood that vout will contain more and more unique values because we have more unique values to choose from as we widen our data distribution. And this is true as we increase vector sizes as well. So when we go to a vector size of 2 to the 11, we see the same trend. So between our between our random numbers between 0 and 10 and 0 and 10,000, our execution time increases from 7.8 microseconds up to 330 microseconds. And for our 2 to the 12 size array or vector, it increases from 30 microseconds for random numbers between 0 and 10, all the way up to over 1,100 microseconds when we're looking at random numbers between 0 and 10,000, a huge increase. Okay, so now that we kind of understand the trends in our baseline, let's see if we helped at all by swapping out our std vector and that linear search of vout when we swap that for our unordered set and that constant time complexity insertion, right? And we see something pretty interesting here. So we can see here our first kind of results. So our 2 to the 10 size vectors with random numbers only between 0 and 10 took about 6.5 microseconds, which is actually slower than our brute force implementation that only takes 2.8 microseconds, right? So unordered set isn't off to a great start. An unordered set copy is around the same as unordered set. It's about 6.4 microseconds. Okay, so what happened, right? We have something that's algorithmically better, but the actual performance isn't that great. So this is where we have to think about the differences between our baseline and our unordered set. So when we have a relatively small or very narrow distribution of our input data, we only have a small number of elements in vout to search through. And with a container like vector, where the memory is laid out contiguously, versus something like an unordered set, where it's scattered right out through memory, it's not allocated as one big chunk, it's actually pretty quick to just search through, say, all 10 elements of vout. Right, so in cases where vout is relatively small, it can be very fast to search vout. Right, so it can outperform something like an unordered set, which is algorithmically better. Right, constant time complexity versus the linear time complexity for std find. So algorithmic complexity isn't the only thing to look at here. However, if we look at, say, as we increase the data distribution, from 10 to 10,000, we start doing a lot better than our baseline brute force implementation. So, for the case of our, random numbers between 0 and 10,000, our unordered set only took 31.1 microseconds to do the filtering, while our baseline took 95 microseconds. So we're about 3 times faster in this case. And this is a trend that continues on for our other cases as well. Right, so if we look at, say, our 2 to the 11 size vector, right, with random numbers between 0 and 10,000, it took 61.7 microseconds for our unordered set. And if we look back at our baseline, that was taking about 337 microseconds, so about 5 times faster. So this is where that algorithmic complexity starts to come in, right? When we're thinking about algorithms and the algorithmic, the time complexity of these things, all that's really saying is that after some point, one of these is very likely to be better than the other, right? But there's some sufficient size number n you have to reach first. And it looks like as we increase, right, the potential number of unique values in our input vector vn, right, we start to see massive gains from using unordered set, which has this O1 or constant time complexity for insertion compared to that linear for std find. Okay, so we definitely see that in most of the cases, right, especially in cases where vout can grow to be quite large or relatively large, our unordered set has the advantage clearly, right? In kind of the worst case for a baseline that took about 1,100 microseconds. Our unordered set only took 123 microseconds, so getting to be about 10 times better. Okay, but what about our unordered set versus unordered set copy, right? What if we need to maintain a vector as an output? Well, if we compare the two, we see that our unordered set and unordered set copy basically mirror each other, right? There's not much difference. In general, what we see is that unordered set copy is only slightly worse than our unordered set. So, in the worst case, right, unordered set copy takes 133 microseconds versus 123 microseconds. So only about 10 microseconds worse for our 2 to the 12 size vector with 10,000 elements. For our 2 to the 11 with 10,000 elements, 61.7 microseconds versus 65. So about a 4 microsecond difference. But as we can see, right, if we compare unordered set copy, we're seeing the same order of gains compared to our baseline brute force implementation, and the same trends that, right, as vout grows, even if we have to copy the elements back to a vector, our unordered set copy is still much, much better, right, than a brute force. With the exception, of course, when vout is very, very small and that brute force doesn't really take much time, right? That linear search is very, very fast. Okay, so that's going to go ahead and do it for this video. There's a lot more things that we could talk about, of course, including some applications of where you might use this, not just from, okay, let's filter something, but after you've filtered something, what problems can you make easier? So we'll look at an example of sorting using filtering next time. There's also some very interesting things to note here in terms of that we could study in terms of branch prediction, right? With branchy, searches and compares, and how that differs between using an unordered set versus a vector, right? So basically using a hash function for indexing, or just a linear scan where we're comparing values. Another very interesting thing to note is, what if you need to keep track of the number of duplicates, right, of each value, or maybe the name of the duplicates for each value, depending on what your input is. Well, in those cases, you could use something like an unordered map, right, instead of an unordered set. So your keys could be the thing that you're filtering, and your values in your unordered map would be things like the count of the number of duplicates, or maybe a vector of the names of the duplicates, right? Of course, depending on what you're filtering. But that's going to go ahead and do it for this time. As always, you can find all of this code on my GitHub page at github.com/coffeebeforearch. So if you go under the repositories, this one will be under the miscellaneous code, and then this will be under duplicate removal, right? So duplicate removal. Okay, but that's going to go ahead and do it for this time. As always, I'm Nick, and I hope you have a nice day.